All right, welcome to The Explainer. Today we're going to talk about something pretty fundamental to artificial intelligence, and that's how does a machine actually learn? We're going to peel back the layers on these things called neural networks and really look at the engine that makes them go.
Okay, let's just dive right in. On the left, you've got nature's own masterpiece, a biological neuron. It's got these little branches taking signals in, a main body that does the thinking, and a long tail to send a new signal out. And on the right, that's the AI version. It's really just a mathematical imitation of the real thing. But the basic idea? It's exactly the same. Some inputs come in, a little bit of math happens, and a result goes out.
So here's the game plan for this explainer. We're going to start with that biological blueprint, then see how these artificial neurons get connected into powerful networks. We'll figure out how they learn from their mistakes and explore this really elegant process called optimization. And then we'll see it all come together in a pretty wild real-world experiment. So first up, let's get a little more specific on that original blueprint, the one inside our heads. So let's break this down, right? The dendrites, the input receivers, are like the x values in our math problem. Each of those inputs gets multiplied by a weight, which is really just a way of saying how important that particular input is. Then the neuron adds up all these weighted inputs. It also adds one more number called a bias. You can think of that as a little thumb on the scale, making the neuron just a bit more or less likely to fire. If that final number crosses a certain threshold, a thing called an activation function says go and sends out the final output. It's a simple idea, but it's incredibly powerful. Okay, so one neuron on its own is, well, it's just a switch. Kind of boring. The real magic, the stuff that makes AI work, happens when you connect millions or even billions of them together. And that's how you get a network. You have an input layer that takes in the raw data, like the pixels of an image. That data flows through one or more hidden layers, and that's where all the heavy lifting, all the complex calculations happen. Finally, it reaches an output layer that gives you the answer, like cat or dog. And when you start stacking up a bunch of those hidden layers, that's when you get a deep neural network. But there's a big problem with these standard networks. They have zero memory. Every single input is treated like a brand new event. As one source puts it, humans don't start their thinking from scratch every second. And for things that happen over time, like understanding a sentence or, say, analyzing brainwaves, that's a total deal breaker. And this is where recurrent neural networks, or RNNs, come in. They have this really clever trick, a loop. This little loop lets the network pass information from one step to the next, which gives it a kind of memory. It can remember what it saw a moment ago to help it understand what it's seeing right now. And this ability is absolutely crucial for the case study we're about to get into. Okay, so we've got our network. But, a network that can't learn is pretty useless, right? It needs to be able to learn from its mistakes. And that is the next giant piece of this whole puzzle. So, for a network to learn, it first has to know how wrong it is. Makes sense, right? We do this with something called a loss function. It's basically just a formula that spits out an error score. If the score is huge, it means the network's prediction was way, way off. If the score is tiny, it was pretty close. The entire goal of training is just to get that loss score as close to zero as possible. And this, right here, is the biggest challenge in all of machine learning. The network gets back this one single number, its error score. But inside, it might have millions or even billions of little knobs to turn, all those weights and biases. How in the world does it know which specific knobs to turn and which way to turn them to make that error score go down? The answer is a process called optimization. And honestly, the best way to get this is with an analogy. I want you to imagine you're standing on a giant, hilly landscape in the middle of a thick fog. This landscape represents all the possible error values for your network. Your goal is to get to the absolute lowest point, the bottom of the deepest valley. But because of the fog, you can only see the ground right at your feet. Now, the most basic way down is called gradient descent. You just look at which way is downhill from where you are and you take a step. But how big a step? That's controlled by something called the learning rate. If your learning rate is too high, you take these huge, clumsy leaps, and you just end up bouncing from one side of the valley to the other, completely missing the bottom every single time. All right, so you think, okay, I'll just take tiny steps. But if your steps are too small, you're just crawling. You are heading in the right direction, for sure, but it would take forever to actually get to the bottom. And in the world of computing, time is money. So what's the solution? There's got to be a better way, right? Well, this is where smarter algorithms come in, like one called Momentum. It does exactly what it sounds like. It builds up inertia, kind of like a ball rolling downhill. It remembers the direction it was just going. This helps it smooth out that crazy side-to-side bouncing and lets it really pick up speed when it's heading straight downhill. And this idea just snowballed. Researchers came up with a whole family of these optimizers, and each one got a little bit smarter. They went from just finding the slope to adding that momentum idea to then getting really clever and adapting the step size for each and every one of the millions of parameters individually. And eventually they combined all of these great ideas into powerhouse algorithms like Atom, which is one of the go-to optimizers that people use today.
Okay, enough theory. Let's see how this stuff works in the real world. We're going to look at an actual experiment where the only thing they changed was the method the network used to get down that mountain.
The experiment they ran is honestly so cool. They used one of those EEG headsets to record a person's brainwaves while they were doing 3 different kinds of meditation. Then they fed that raw brainwave data to a recurrent neural network and said, okay, figure out which meditative state this person is in right now. So the big question is, does it really matter which path you take down that metaphorical mountain? Does the optimizer you choose actually make a difference? Oh yeah, it matters. A lot. The results are just, wow. They're dramatic. Look at this table. The Eta Delta algorithm got it right only 34% of the time. That's basically just guessing. But on the other end, you have Atom, that smarter algorithm, hitting 83% accuracy, using the exact same data and the exact same network. That's a huge difference.
And if you're a visual person, these charts, they're called confusion matrices, they make it crystal clear. What you want to see is a strong, dark diagonal line. That means the model's prediction matched the real answer. The chart on the left for Eta Delta, it's a mess. It's confused, it's guessing all over the place. But look at the one on the right. That clean, strong diagonal line tells you the model is nailing it, confidently and correctly telling the different meditation states apart.
But wait, there's one last twist, and this is maybe the most important part. The researchers decided to run the tests again, but this time they took the time to carefully tune just that one setting, the learning rate, or the step size, for each algorithm. And just look what happened. Eta Delta, our worst performer, skyrocketed from a measly 34% all the way up to 82% accuracy. It suddenly became one of the best. So what's the big takeaway here? It shows that the algorithm you pick is only part of the story. How you guide it, how you set its path down that mountain is absolutely critical. We've just seen that when it's guided correctly, a machine can learn to tell the difference between subtle states of human consciousness just by looking at brainwaves. It kind of makes you wonder, what other incredible hidden patterns are out there in the world, just waiting for us to find the right path to discover them?